Good morning, folks, and welcome to another one of our Cosmic Conversations. My name is Josh. I'm part of the Morrison Planetarium team at the California Academy of Sciences, and we are so excited to be joined by Dr. Stephen Jarrett from American Museum of Natural History. Hi, Stephen. How's it going?
Good. How are you, Josh?
It's been a wonderful day so far, but I think we're a little toastier on the West Coast than the East Coast, it sounds like.
It was cold this morning.
For your presentation, we wanted to focus on some of the things that travel around Earth, the things that hang out in space. We call meteorites, meteoroids, comets, asteroids. It's a big family. Can you tell us about your expertise within it?
Sure. So I'm it's called a planetary geologist. So I study the rocky objects in the solar system, particularly focused on the Earth, because last time I checked, Earth is a planet too. And my specialty is to understand what happens when large objects crash into Earth. So I focus mostly on the effects of these large impacts, looking at impact structures here on the Earth, but also dabble a little bit into understanding what those objects were, what the comets or asteroids were, and what the samples, if they don't get completely destroyed in making a crater, some of the meteorite samples that we have as representative objects from space.
So there's a specific impact that I know is near and dear to our hearts for the Morrison Planetarium team because it was something we featured prominently in a show. So I'm going to turn it over to our producer, Mary, to show us an actual impact from our presentation incoming, which is a really fun thing to see. So let's check that out.
With one such event in...
So we are flying with a bird, which is a CG bird, at the edge of a very special site here in the US, which is called Meteor Crater. And this is a place you've actually visited, right?
Yes. And I should say that it's commonly referred as Meteor Crater. The official name is the Barringer Crater, named after the Barringer family and person who first identified this important structure.
So we've heard a legend that it had the name Meteor before folks really knew that this was an impact site. Is that true?
I don't know the specific timing of when it was identified and referred to as Meteor Crater, but yes, this is a crater that was known about long before we realized that it was actually a meteorite crater. And there's a whole long, really interesting history about sort of the discovery of this and identifying it as a meteorite crater.
So if we switch over to our software, we can actually see this from above in satellite photography. So we are showing this to you via the Open Space program. If this is something you find really interesting for you viewers at home and you want to check out, by all means, head to openspaceproject.com, download it for yourself, install it, play around with it, and eventually, you get real good, you can find cool stuff on the surface of planets like Earth, like this feature. So I love checking out, you can see sort of a squiggly dark line here. That's a road. And Stephen, is this a visitor center off on the side?
Yes, there's a building there, a visitor center. It's a really great museum. If you're ever there when it's safe post-pandemic, definitely it's a fantastic museum and goes through a lot about crater science and the history of the crater. It was first identified by Barringer, who was a mining geologist and thought it was an impact and was sort of convinced that he would be able to mine the iron from the meteorite that would have formed it. And that didn't turn out as he had hoped. And one of the things that we didn't know back then, this is in the early 1900s, is that when you have something like this, where it's actually a meteorite crater, when it lands, there's so much energy, it's such a big explosion, that the rock itself is largely destroyed in that event itself. Now, at Meteor Crater, there have been meteorites that have been recovered. It's known as the Canyon Diablo meteorite that a lot of museums have pieces of.
We do.
And a lot of those are scattered around in pieces and sort of were found outside the crater. And even though some of them are big pieces, right, they're only a tiny fraction of the actual full object that hit. The object that hit was probably about the size of a school bus, maybe a little bigger. And made a crater that's about a mile across.
Wow. Now, when you mentioned the size of the crater, that reminded me, this is a very square crater compared to kind of the stereotypical very round crater we might imagine. Is that a naturally occurring feature? What's going on here?
Yeah, it's somewhat unusual, and it's a good reminder for us geologists that what you're dealing with when you have something hitting the Earth is there's existing rock there, there's existing structure there. And so this impact is fairly recent, about probably 50-ish thousand years ago. So there was the rocks there had already formed, and they're part of this volcanic plateau of the Colorado Plateau. And as those rocks formed, the volcanic rocks formed, they cooled in such a way that there's a pervasive set of jointing in the rocks itself. So there's this pre-existing network of these fractures that when it hit, it took advantage of that weakness, and sort of there are these big tears in the sides and the corners, taking advantage of the pre-existing rock. So you always have to think about what got struck like.
Very cool. So when we look around, you really don't see anything else like this. It's kind of a unique feature, as opposed to when we look at the moon or Mars, where you can see dozens or hundreds of craters in a given region.
Yeah,
they're rare on
here,
Earth.
They're impact craters are rare on Earth. But one of the things about meteor crater that was part of why it took so long to be identified as a meteorite crater is there are volcanic craters nearby and in the area. Some of the prominent ones you might have heard of, maybe Sunset Canyon, some Sunset Crater. Northern Arizona has a lot of these volcanic craters. And in a lot of ways, at least, first glance and sort of initial looking, the volcanic craters and impact craters can look sort of similar in shape.
Oh, my computer seems to be unhappy with what I'm doing to it, so I'm going to back off a little bit. Okay, and now we wanted to show off some of the other sort of less visible craters we might be spotting. I'm going to take us over to...
It looks like we had a question. Do we want to, while you're doing that, do we want to answer?
Sure.
I can, this is a great question.
What's between meteorite, comets, and asteroids? So when we've got these distinct groups of objects, how would you describe them?
Right. So it's a little bit about what it's made of and mostly where it is. So out in space, rocks that are largely rocky material out in space are called either asteroids if they're big, or if they're small, like head size, what sometimes call them meteoroids. Once they've come into Earth's atmosphere, when they're traveling through the atmosphere and glowing like a shooting star, we call those meteors. And if it hits the ground and you can pick it up as a rock after, we call that meteorites. And comets, on the other hand, are out in space, usually really far away. A lot of them start out at orbits beyond Pluto, but they're largely icy. You can think of them as maybe like dirty snowballs, where they're mostly ice with a little bit of rock, but still out in space.
Fantastic. I think we will have a chance to see some of those different representatives of those different families in just a little while, as soon as we pull away from Earth. But I'm looking around here. I've been assured this is the correct location on Earth, but I'm really not seeing a crater like we saw before.
Yeah, and we're at a location in Norway. That's where I did some of my master's work, at a crater. And this really highlights one of the reasons why Earth is different from the moon and is not covered with visual craters. Earth's surface is dynamic, first of all. So you have things like plate tectonics and erosion and surface processes that change the surface. But also, look at all these trees. Look at all this cover. This is so different from the desert of Arizona, right? The other thing here in the foothills of the mountains in Norway is there's a lot of other structure. It's not just a flat desert. So it's really hard to see some of the differences, particularly when you're dealing with old craters. This crater, instead of being 50,000 years old, this one's probably close to 500 million years old.
Wow.
And so it's really hard to see the crater. But we do know it's there. I mean, the first way is you go there and visit, and there's a sign telling you this is a...
That's helpful.
Yes. There's a really nice museum that the local town put together about the crater. But other than the sign, you actually can go and look at some of the rocks. I think I have some pictures, too, of the rocks. And there's a very distinctive set of textures in these rocks that are unusual for the area. There's another one also that I think is pretty fun looking. Yeah, this is what we call a breccia, where all of these sort of were just ground up and pulverized by the impact itself. Very different from the surrounding rocks, and you can see this really well in the field.
So this is shattered rock that liquid rock kind of flowed into or around and then resolidified?
It probably wasn't liquid. There's a little tiny bit of material there that got melted, but this is mostly just pulverizing and grinding rocks back against each other.
Wow.
And sometimes they're easy to find. Sometimes it's a little bit more difficult. One of my favorite parts of being out there was playing the game of Find the Rock. A lot of it's covered. A lot of it's covered in moss. So this is me peeling off a big sheet of moss to expose some of the rocks beneath. But this is pretty typical of that terrain in Norway, where you're climbing around in the mountains, and it's really hard to recognize. A lot of people drive through the area and don't even know that there's a crater there.
So, and once in a while, we'll get an impact that doesn't even leave a crater behind, right? We have a clip from one of our presentations, I think. Of an air explosion?
Yeah, airburst. Right? Airbursts.
Airburst. So we've been telling people that this is about the size of the Morrison Planetarium when it came in through the air, just to give you a sense of context. And as it's interacting with Earth's atmosphere, you can see it starting to heat up. You get that nice glow around it. And that's part of the explosion right there. So when it shatters, you get all those bits flying off. Those individual pieces might strike Earth too, but they're a lot smaller and lower energy. The real explosion happened right where you see these blue waves propagating outwards from.
Yeah. And this is a really probably more important part of our cratering record than we realize. One of the things we've seen this was Chelyabinsk that happened, fairly recently. I can't remember what year, but relatively recently. Something like 13 or 14, yeah. This has also happened before. The most famous is what's called the Tunguska event about 100 years ago. And the thing here is, since it doesn't actually hit the ground, it breaks up in the atmosphere. That can do a lot of damage. I mean, from Chelyabinsk, there were windows that were shattered. I mean, it was a really big explosion. But it didn't hit the ground, and so it didn't make a crater. And one of the challenging things from a geology perspective is, over time, even craters, like you saw the one in Norway, even that was a crater, gets eroded away over time. And so how do you recognize these events when you have no record of them on the ground? There probably were many more of these over Earth's history. There's some impact material that we see from various parts of the world, the most famous being what's called the Libyan desert glass, where there's this glass found, and it's speculated that this was melted by the effect of an airburst. There were probably a couple other of these over the Earth's history, but it's really hard to say because we don't really have that direct hit.
Well, I love, when we're talking about craters on Earth, I love visiting this one because it is so obvious. But when we were rehearsing, you mentioned that this crater Manicouagan is sort of artificially obvious.
It's helped artificially. I mean, the structure is still there, but the water there has been dammed as part of a hydroelectric plant. And so that's certainly, having the water there occupying the trough makes it easier to see, but it still would be there. It's not an artificial crater. But what's cool about Manicouagan,
planetarians.
Yes. What's cool about Manicouagan is that it's so obvious and so big that the astronauts in the space shuttle would be able to see it from orbit. And I've been told that they would use this as something for targeting on re-entry when they were coming back in, because it's such an obvious target.
Sure, and unique again in the landscape. You don't see anything else like it.
Yeah, and Manicouagan's a really fun crater. It's a crater that I have worked on samples from for part of my PhD. I really want to go. I want to go to Manicouagan so bad. It's hard to get there, and it's not easy terrain to navigate when you're up there. But one day,
as we're post-disease restrictions, I hope you get out there. So when we talk about the samples from these things, we can learn a lot about the object that created the impact, but we can also associate it with some of the other families of objects in our solar system. Can you tell us about what makes a family of asteroids or a family of meteorites?
Yeah, so the asteroids, we classify asteroids and meteorites a couple of different ways. For both asteroids and the meteorite rocks we have, we do it a lot based on composition. So what it's made of, its chemistries, the textures, and there are different kinds of meteorites. There's some that are what we call stony meteorites because they're made of mostly stone-like material, silicon, aluminum, sodium, those kinds of elements. There are some that we call irons because they're made predominantly of nickel and iron. And this one, you're never going to guess what we call this one. It's the one that's made of both stony material and iron material.
Let's see, stony iron meteorites?
That would be correct.
I love it when scientists get creative with it.
Occasionally, geologists come up with silly names, but occasionally we get them with pretty obvious names. So that's how we classify the meteorites. And asteroids, we classify a little bit based on their composition and also based on where they are. So there are things like what we call the main belt asteroids, which occupy the region sort of between Mars and Jupiter.
I can show you the inner main belt, but I've noticed my computer gets really unhappy when I turn on the main belt. So here's our best representation of some of that family.
And there are just so many. I mean, this is the thing that I always get really, I forget until you see visualizations like this, just how many asteroids there are out there. This is just one type. But when you think about, particularly when you read in textbooks or in school about the asteroid belt, it makes it seem like it's not that much. But there's so many objects out there. It's really, space is not that empty. So we have the main belt asteroids. We have Trojan asteroids, which are ones that share orbits with Jupiter.
You can see them right out here.
Yeah. And then we have the ones that I call Earth orbit crossing asteroids, or sometimes referred to as potentially hazardous asteroids. And these are all asteroids whose orbits cross the orbit of Earth. And that's important because if Earth is at the same part of the orbit that the asteroid crosses at the time when the asteroid crosses it, well, that's bad, right?
Yeah.
You don't want the asteroid to be at the same place as Earth. And so there's a whole network of astronomers and planetary geologists and planetary defense folks at NASA who are actively tracking and watching and keeping an eye on these potentially hazardous asteroids.
If anyone is really interested in this, and I think pretty much everyone should know what humans are doing to mitigate this threat, we had a cosmic conversation a couple weeks ago with Dr. Ed Lu, who is passionate about making sure the planet doesn't get smushed while no one's looking.
Yeah, and there's some really interesting missions and things that are being put forward. There's a whole group called the Planetary Defense Community and Planetary Protection, and it's all kinds of things and ideas of like, okay, what would you do? And they're the ones, of course, like, Bruce Willis goes and blows it up kind of thing. But there are a lot of other ideas that it ranges from shining light onto them to heat them up, and that would change its internal energy and change its orbit. There are ideas of flying some really massive object next to it to create a new center of mass, which would change the orbit slightly. And I was at a meeting several years ago, and with one of these ideas that came up, and somebody got up and asked the question of, oh, well, that sounds like, will this really work? Will that really move it enough? And spoken like a true physicist, he says, well, you only if you do it when it's far away enough, you don't have to move its orbit very much.
There you go. Just a tiny thing to push it out of that keyhole.
My favorite of these missions, if you want something to look up, is called the Gravity Tractor. I think that's just like the coolest name for a mission.
It for sure is either very evocative of farming equipment or like a tractor beam from Star Wars or Star Trek. So I like it a lot. So we had an object you called out specifically called Cleopatra.
Yeah.
And I wanted to fly us there just because for our audience, I want you to imagine what the shape of I guess you'd call this one an asteroid would be.
Yes.
So what is an asteroid shaped like? Hold that in your mind. And now we're going to go visit the shape of one. We don't have great high resolution imagery to show you, but you can see the shape of this thing quite clearly. And boy, it does not look like I imagine an asteroid would look like.
And I should point out when part of the reason that we don't have super great high resolution imagery is not the fault of either Josh or I or the planetarium, right? This is a thing about, asteroids are really far away, and we've not visited very many up close.
Mm-hmm.
lately in the news, it's been a good couple years for asteroid science in the news. So it's easy to forget that out of the numbers of objects out there, there are very few that we actually have really good close imagery of.
And I think we're going to spoil ourselves later, but I thought this one just has such a funny, like, my dog loves chew toys, and this looks like one of those chew toys.
Do we have the still image of Cleopatra? I don't remember if that was one thing we
Let's
had in here.
see. Mary, do we have anything in the queue? We might be able to fish one out for later, but for right now, let's go visit one of the objects that we do have some better imagery of. I'll give it your choice, Stephen. Vesta or Bennu?
Let's go to Bennu.
Okay, so targeting Bennu. This is again in the asteroid belt, I recall.
Yeah.
Oh, this is relatively close. This must be one of the Earth crossing.
That's correct. It is. I believe it is an Earth crossing orbit asteroid.
Wow.
And this is one that's been in the news lately because of the NASA OSIRIS-REx mission. Some of you may remember a couple months ago where we sort of did a high five with an asteroid and collected some sample. And that was a really exciting mission. I'm super excited about it, particularly because not only did we get great imagery of this object when we orbit it with really high resolution imagery, but when we did the high five and collected some of that sample, that material is going to come back to Earth. And we're going to be able to study that material here on Earth. We have some idea of what we think asteroids are like based on our meteorite sampling, but those were delivered to Earth by physics, right?
Right.
And so one of the big questions in planetary asteroid meteorite science is how representative is that of the asteroid belt? Is there, our meteorite collection, how much of that is biased because there might have been one event or something that threw a lot of similar material to us? And so it's really kind of a different question when you're going out to something that never was super close to Earth and you're collecting something and bringing it back. Will be really interesting. And
one of the things
looking at it is just crazy.
For looking at the composition, yeah, that's the point I was going to make. This seems really tactile to me. So when you look down on that, it really looks like the pile of broken rock and scree you see at the bottom of a mountain in like Yosemite or something, where you get all that broken rock piled up.
So there's a term for this kind of asteroid. We call it a rubble pile because it looks like a pile of rubble. And in the asteroid science, there sort of has been this idea of that was put forward of rubble pile asteroids as being one of the possible ways that these asteroids form. And this was sort of a surprise to many when we got up close with the mission to see exactly how rubble pile-y this was. Going in, it wasn't clear to everybody, and not everyone thought that it was going to be a rubble pile. When we got there, it certainly is.
And when you
there are a
pick
lot of
out
cool
some
questions
of
about,
standout features, you can see like individual large blocks that are just hanging out on the surface. They're not mountains or anything that was formed through like a geological process, right? This is just a big rock that stayed there.
Yeah, and so there are a lot of questions about how you get a rubble pile, like physics-wise. How do you make this, and how do you keep it together, right? How do you have enough gravity to keep all of these things together as from a distance, a relatively uniformed shape? Like from a zoomed-out view, this looks kind of almost ball-shaped, right? And then you get down close at it and look, and it's got enough gravity to hold itself together, but it's clearly broken up and fragmented. And that, I think, is going to be really interesting when the work starts coming back on this, of how we think that affects what we know about the object. One of the ways that we think we understand what asteroids are made out of is the density. Things that are high density, like iron, or things that are low density, some of the lighter elements like silicon, aluminum, calcium. But pore space plays, and space between rocks plays a large role in density. So if this ends up being, lots of pieces loosely connected to each other, that could change the density enough to sort of throw us off into what we thought it was made out of.
That there would just be a lot of, I guess, like
you
really
could
low
have,
density because they'd be vacuums.
Yeah. And so that mix of lots of rock and nothing would end up, averaging out to a different density than we would expect.
I'd imagine holding like a small piece of granite versus a small piece of pumice. The pumice is going to weigh a lot less because it's got
Right,
those
because it
empty
got that
spots.
space in it, yeah. And so maybe with some of these big rocks, if they're, depending on what's between them, it might be sort of more empty than we realize.
So this is, I would hesitate to call it round for Bennu. To me, it kind of reminds me of the shape of a D10 for any tabletop players out there, but it's got that nice wedge shape around the edge. Is that because it's rotating?
That's a good question.
It seems so well lined up with the plane of the solar system. I'm always tempted to attribute it to that.
I'm less of a physics dynamics person, so that's probably, I'm not the best one to answer that.
Fair enough. We do have another object with a very interesting shape that I think is more impact related, that is Vesta.
Yeah.
I always think that is one of the coolest things in our solar system, and its connection to the rocks we find on Earth is just amazing.
Yeah, I'm a big fan of Vesta, particularly because this is a case of there's one type of meteorites that we have on the Earth. It's actually a set of a couple of groups. There are what we call the Howardite meteorites, the Eucrite meteorites, and the Diogenite meteorites. And we think they all came from the same object. And we're pretty sure that that object is Vesta. And in addition to doing some special chemistry arguments, and you can look at what the object looks like when you look at the spectra coming at it through a telescope, that match, but also there's a really large crater at the bottom. And
I think I can line us up so we can see that flat region pretty well.
And so it's this combination of Vesta being a large object that could be big enough to have produced those kinds of meteorites that we have, and it having the same spectral signature and chemical signature, and an obvious look, there's clearly something missing. Sort of all goes into this idea that we're pretty sure that these meteorites can be traced back to either this asteroid or one of its family asteroids.
You can even see some of these long lines across the surface that are sort of parallel to the plane of where we think that impact was. But the whole thing looks like it's a can that got scrunched together.
Yeah, and there's a little central peak on the other side. It's the lighting, finding a good image and lighting is hard. But yeah, it's like a little dimple at the center of that crater.
There we go. There's a crater.
Yeah.
So this is just an amazing object, and one that I love looking at it from this angle. It looks completely round, like a Ceres. But then you look at it from this angle, 90 degrees in one direction, and it's
nope, surprise. and this was another one that was visited by a NASA mission. The Dawn spacecraft and Dawn mission visited Vesta, and the other one you mentioned, Ceres. So there's lots of good imagery data that came back from those.
Well, thank you so much for letting us kind of wander around the solar system with you and pick your brain. This has been really cool to find out about the objects that strike Earth and sort of tracing them back to the families they came from. Is there anything else you'd want to leave our audience with?
I just want to thank everyone for watching. This has been really fun. If there are any questions, I'm happy to take some more questions if we have.
I saw we had a couple pop up. Does this object rotate? So let's think about for Vesta and for Bennu. You mentioned there might be some element of rotation, but you'd want to look that up.
Yeah, they're definitely rotating. I don't know if that rotation affects the surface features you see, but they are rotating.
So my guess would be that if it is sort of the more rubble piley, then it would bulge out in the middle if it was spinning fast enough. But that's based totally on a notion of mine and not evidence. Is the Kuiper belt in the outer reaches like near Pluto? I think we have a couple Kuiper belt.
Yes, it is. And that's a very good question. That's exactly correct. Pluto is within the Kuiper belt, and I like to think of Kuiper belt objects, and to some extent also Pluto. But the Kuiper belt objects are sort of these frozen asteroids. Mostly a lot of icy material, a little bit of rock, sharing the orbit out there with Pluto.
It looks, again, kind of like you mentioned with the asteroid belt, like there's a lot of objects, but sometimes you can pick out one specific region where it looks like there's a big stripe of just way too many objects, in one spot. And I thought this was really cool, like some kind of, I don't know, wave of material passing through. But I believe one of our experts pointed out that that's just where we pointed the Hubble telescope. And we saw a whole bunch of objects.
Yeah.
It's a lot easier to explain than some giant wave of asteroids flying through the Kuiper Belt. Let's see, any other questions pop up? Well, thank you so much, Stephen. This has been an absolute pleasure. And for our friends at OpenSpace, thank you for letting us broadcast out. So if you're watching via the OpenSpace YouTube channel, you can check out more of our programs happening on our Facebook page. If you're watching from our Facebook page, go check out OpenSpace YouTube. There's a lot of cool programs happening there too. But on behalf of myself and Morrison Planetarium, Stephen, thank you so much for joining us. Have a wonderful rest of your day.
Thanks for having me. This was really fun.
See you later.